Introduction. Ventilation modes, or simply modes, are a hot topic of mechanical ventilation. At almost every related professional congress, someone talks about modes. However, ventilation modes remain mysterious and confusing. There is a strong need for a simple and clear description of ventilation modes, including the definition, classification, indications, and so on. This learning module is to explain them. Before starting this module, we recommend that you view 3 basics modules in this sequence: lung ventilation, natural and mechanical, ventilator system concept, essential variables, and mechanical breath types. This module will take about 35 minutes to complete. Mode is a part of ventilator settings. Ventilator settings are the operator's commands to the ventilator. They define how the ventilator should perform. It is often necessary to modify the settings when the patient's clinical condition or therapeutic strategy change. There are several categories of ventilator settings. Each defines a specific aspect of ventilator operation. Common ventilator settings are ventilation mode, control parameters, and alarm limits. Mechanical ventilation therapy is optimal only when all settings are appropriate. What is a ventilation mode? Most ventilators today share a common operation principle: intermittent positive pressure ventilation, IPPV. In this module, we will focus on ventilation modes with this principle only. Intermittent positive pressure ventilation is realized in form of a series of mechanical breaths delivered by a ventilator system. As we learned in the last module, essential variables and mechanical breath types, there are 8 types of mechanical breaths. A ventilator system performs very differently, dependent on the deployed breath type and their sequences. A ventilation mode is defined as a set of predefined breath type or types and sequence. Every mode has its own intended applications. A modern ventilator usually provides several ventilation modes to meet various clinical conditions. Only one mode can be used at a time. When you select a mode, it means that you consider it to be the most suitable for this patient now. The ventilator simply obeys your order. We will discuss mode selection in depth in Section 11, Bedside Mode Selection. Modes and control parameters. Control parameters, or simply controls, are another category of ventilator settings. Modes are designed to define the breath type and sequence, while controls define the main properties of the defined breaths, including triggering, cycling, controlling, targeting, baseline pressure, and FiO2. Every mode has a unique set of controls. Controls can be roughly classified into 3 groups: those for ventilation, those for oxygenation, and those for synchronization. The table shows the common controls in each group. A modern ventilator usually has a default mode and its default control settings. The defaults are designed for quick start of mechanical ventilation. Yet, if not in a hurry, you should set the mode and controls individually for each patient. Why so many modes? It is hard to tell the total number of ventilation modes. According to Chatburn, a top expert and educator in mechanical ventilation, there are 174 unique names for modes of ventilation. Why do we have so many modes? This phenomenon comes mainly from the technological evolution and non-standard nomenclature. At the very beginning, ventilator design was simple and rigid. Ventilators worked well only in a passive physical model. When a ventilated patient breathed actively or his or her clinical condition changed, asynchrony was inevitable. If this occurred, the operator only had 2 options: either to adjust the settings around the clock or to suppress the spontaneous breaths. Neither is a good option. To solve this problem, the ventilator industry constantly introduced new modes, some useful and some less useful. Only a few good ones stand the test of time. Naming of ventilation modes is not globally standardized. Ventilator manufacturers are free to name the modes in their ventilators. Here we need to differentiate between unique mode names and unique modes. The number of unique mode names is much bigger than that of unique modes. The worst scenarios are that one unique mode has different unique mode names, and that one unique mode name is used for different unique modes. A name is just a label for identification. If a name fails to do this, we have to analyze the primary characteristics to differentiate one subject from the others. If it walks like a duck, quacks like a duck and looks like a duck, it must be a duck. In terms of ventilation modes, the characteristics are breath type and sequences. Mode classification. All IPPV modes can be roughly split into 3 categories: traditional modes, advanced modes, biphasic modes. We will explain traditional and advanced modes in this section, and describe biphasic modes later. Traditional ventilation modes. Traditional ventilation modes are also known as conventional modes. They are relatively simple, mature and most widely used. You will find them in most ventilators, possibly under different names. If we don't consider the differences in the naming and other minor technical details, we can identify 8 unique traditional modes in 3 groups. Continuous mandatory ventilation modes, SIMV modes. Synchronized intermittent mandatory ventilation modes, SIMV modes. Support modes. SIMV modes have 2 subgroups: assist control modes, AC modes, and genuine SIMV modes. The 2 groups are identical except for the patient trigger. Patient trigger is possible in AC modes, but not in genuine SIMV modes. In this learning module, the term SIMV modes refers to AC modes because AC modes can fully replace genuine SIMV modes in clinical practice. AC modes become genuine SIMV modes if patient trigger is turned off. Hamilton Medical ventilators do not offer genuine SIMV modes. Some ventilators from other vendors may still provide genuine SIMV modes. Each mode group has 2 or 3 modes. The modes in the same group are the same in indications and contraindications, triggering, cycling mechanisms, and breath sequence. The only difference is the controlling mechanisms. We will explain the individual traditional modes in depth in the next section. Advanced ventilation modes. Advanced and traditional modes are common in breath types, yet, advanced modes have much more complicated controlling algorithms. Advanced modes are designed with 2 ultimate goals: to improve the quality of therapy and to unburden the clinical staff. These goals are achieved by applying various forms of automation. In an advanced mode, the ventilator is able to automatically adjust some ventilator settings according to the operator's commands and the monitoring input. This table lists the major advanced modes that are commercially available today. In this basic learning module, we will not explain the advanced modes any further. If you are interested in the Hamilton Medical's advanced modes, view the learning modules about ASV and INTELLiVENT-ASV. A close look at traditional modes. In this section, we describe in depth the traditional modes in groups based by analyzing their breath types and sequences. To make the information easier to understand, 9 breath symbols are used. Note the key characteristics. A volume breath is identified by its unique shape. An adaptive breath is identified by the double arrow at the inspiratory pressure. Patient triggering, either pressure or flow, is indicated by a red circle at the beginning of inspiration. Flow cycling is indicated by a blue circle. An unsupported spontaneous breath has a negative inspiratory pressure and then a positive expiratory pressure. SIMV modes. As mentioned earlier, SIMV modes here refer AC modes but not genuine SIMV modes. A SIMV mode comprises 2 breath types. VTMB stands for ventilator triggered mandatory breath. It is time triggered and time cycled. PTMB stands for patient triggered mandatory breath. It is flow or pressure triggered and time cycled. Please remember the 2 abbreviations, VTMB and PTMB, as they will be used repeatedly later. Both VTMB and PTMB can be volume-controlled or pressure-controlled or adaptive-controlled, forming three individual CMV modes: volume CMV, pressure CMV, and adaptive CMV. In a CMV mode, both VTMB and PTMB are always the same in controlling mechanism. CMV modes are widely used. They are indicated for both passive patients and partially active patients. It is a possible, but not optimal choice for active patients because patient-ventilator asynchrony may occur. In CMV modes, an operator must set the backup rate for VTMB. If no valid patient trigger is detected, the ventilator regularly delivers a VTMB at the set rate. If a patient trigger is detected just before a scheduled VTMB, the ventilator delivers a PTMB. In this way, the patient can control the actual rate, which is usually higher than the set rate. Under normal conditions of use, CMV modes behave in one of three possible scenarios. If the ventilated patient is passive, all breaths are VTMB. If the ventilated patient is partially active, there may be a mixture of VTMB and PTMB. If the ventilated patient is active, all breaths are PTMB. Typically CMV modes have the following controls: rate, TI or I to E ratio, patient trigger type and sensitivity, tidal volume for volume CMV, pressure control for pressure CMV or target volume for adaptive CMV, pressure ramp or rise time for pressure CMV and adaptive CMV, PEEP, FiO2. Volume CMV mode may have two additional controls: flow pattern, inspiratory pause. SIMV modes. SIMV stands for Synchronized Intermittent Mandatory Ventilation. They are among the most frequently used modes. SIMV modes evolved from IMV modes, intermittent mandatory ventilation, and almost replaced them completely. SIMV modes comprise three breath types: VTMB, which is time-triggered and time-cycled; PTMB, which is flow or pressure-triggered and time-cycled. SB stands for spontaneous breath. It is flow or pressure-triggered and flow-cycled. In all SIMV modes, SB is always pressure-controlled. Remember the abbreviation SB as it will be used repeatedly later. VTMB and PTMB can be volume-controlled or pressure-controlled or adaptive-controlled, forming three individual SIMV modes: volume SIMV, pressure SIMV and adaptive SIMV. Note: in a SIMV mode, both VTMB and PTMB are the same in controlling mechanism, yet SB is always pressure-controlled, though the support can be set to 0. SIMV modes have two unique features. First, the set backup rate for VTMB can be very low, for instance, 1 or 2 breaths per minute. Second, the set rate and TI determine the interval between end of inspiration of a VTMB or PTMB and beginning of the next VTMB and PTMB. If the interval is sufficiently long, one or more SB may be inserted, with or without pressure support. This is not allowed in a CMV mode. Let's look at two typical SIMV examples where the ventilated patient is active. If the set rate is 15 breaths per minute and the set TI is 1.3 seconds, the resulting interval is 2.7 seconds. This is too short for insertion of even one SB. In this case, SIMV modes act like CMV modes. If the set rate is 2 breaths per minute and the set TI is 1.3 seconds, the resulting interval is 28.7 seconds. This is sufficient to insert several patient breaths. In this case, SIMV modes act like a pressure support mode. Therefore, by setting the backup rate, SIMV modes may suit all ventilated patients, passive, partially active or active. This is why SIMV modes are sometimes called universal modes. In a passive or partially active patient, we should therefore set a relatively high backup rate to ensure adequate ventilation. In active patients, We should set a low rate to improve patient comfort and promote the patient's spontaneous breathing. A very low rate is prohibited if the patient is passive. Under normal conditions of use, SIMV modes may behave in one of 5 possible scenarios. 3 of them are associated with a high set rate, and the remaining 2 with a low set rate. At a high set rate, SIMV modes act very similar to CMV modes. If the patient is passive, all breaths are VTMB. If the patient is partially active, there may be a mixture of VTMB and PTMB. If the patient is active, all breaths are PTMB. At a low set rate, the interval is long so that SB can take place between 2 consecutive PTMB. The SB may be pressure supported or unsupported. In these cases, SIMV modes act like pressure support mode. Typically, SIMV modes have the following controls: rate, TI or I to E ratio, patient trigger type and sensitivity, tidal volume per volume SIMV, pressure control for pressure SIMV or target volume for adaptive SIMV, pressure ramp or rise time for pressure SIMV and adaptive SIMV, flow cycle ETS, PEEP, FiO2. Volume SIMV mode may have 2 more controls: flow pattern, inspiratory pause. Support modes. This group has 2 modes, pressure support mode and volume support mode. Each has just one breath type, pressure SB for pressure support mode, and adaptive SB for volume support mode. In support modes, there is no backup rate. The ventilator delivers a spontaneous breath immediately after a valid patient trigger is detected. Otherwise, it keeps waiting. Therefore, support modes are indicated for active patients only. Always enable apnea backup function in a support mode for patient safety. Pressure support mode. This mode is also known as SPOND, PS or PSV. We use SPOND thereafter. SPOND mode is widely used, and is the most comfortable for active patients among all traditional modes. Pressure support, P support, is a critical control in this mode. By setting it, you define the level of ventilator support for patient breaths. If P support is set reasonably high, SB are adequately supported. In this way, pressure support mode suits active patients who cannot yet do all of the required work of breathing. If P support is set to 0 or close to 0, the patient breathes spontaneously at PEEP, with no or little machine support. This suits the active patients who have stable and strong breathing activities. Such an application is typically used for weaning. Volume support mode. The volume support mode is derived from the pressure support mode, and is relatively young. Its clinical benefits and limitations are not yet fully known. Target volume is a critical control of volume support mode. The ventilator automatically regulates the inspiratory pressure after every breath to match the monitor tidal volume to the set target volume. You need to adjust the setting of target volume to meet the patient's ventilatory demand, which may change over time. Failure to do so can lead to unwanted hyperventilation or hypoventilation. The volume support mode has just one possible scenario. Typically, support modes have the following controls: patient trigger, type and sensitivity, P support for pressure support mode or target volume, V target for volume support mode, pressure ramp, P ramp, flow cycle ETS, PEEP, FiO2. Biphasic mechanism and modes. Biphasic modes are the third mode category. Before talking about biphasic modes, we need to learn biphasic mechanism. Mechanical breaths, the basis of IPPV, can be generated in 2 ways: classical mechanism or biphasic mechanism. Classical mechanism. The classical mechanism was described in the module Ventilator System Concept. In short, during inspiration, a ventilator opens the inspiratory valve and closes the expiratory valve, causing the airway pressure to rise. During expiration, It closes the inspiratory valve and opens the expiratory valve, causing the airway pressure to drop. As such, the two valves always act in opposite ways. However, this mechanism cannot generate PEEP. A special PEEP generating mechanism must be added. During late expiration, the desired PEEP is generated by the interaction between the declining expiratory flow, delivery of a constant base flow, and regulation of the expiratory valve for an appropriate level of resistance. This mechanism is sometimes called active exhalation valve. Biphasic mechanism. The biphasic mechanism is an extension of the PEEP generating mechanism. You can find PEEP control in all ventilation modes. Let us do an exercise. Set PEEP to 5 centimeters of water. Wait for 4 seconds. Increase PEEP to 20 centimeters of water. Wait for 2 seconds. Repeat the above steps sequentially. The activities cause the PEEP to alternate between 5 and 20 centimeters of water in a specific time pattern. The resulting waveform is very similar to that of a pressure mode. This proves that mechanical breaths can also be generated by PEEP generating mechanism. For this application, PEEP alteration is called biphasic mechanism. In biphasic modes, PEEP alternation is automated. For that we need 4 special controls: PEEP high, PEEP low, PEEP high time, PEEP low time. Initially, the biphasic mechanism was applied to non-invasive ventilators. There, the PEEP high and PEEP low are sometimes called inspiratory positive airway pressure, IPPV, and expiratory positive airway pressure, EPAP. The major advantage of the biphasic mechanism, at least in theory, is better patient comfort and synchrony because the ventilated patients can breathe or even cough anytime at either PEEP level. This is not possible with the classic mechanism because the expiratory valve closes during inspiration. However, with biphasic mechanism, a ventilator consumes much more gas than the classical mechanism for the same application. By definition, PEEP counts from 0 or atmospheric pressure. This also applies to PEEP high and PEEP low. In a pressure mode, however, the inspiratory pressure, that is, P control or P support, counts from PEEP. Therefore, in a pressure mode, the peak pressure is the sum of P insp and PEEP, while in a biphasic mode, the peak pressure equals PEEP high. If you are not sure how inspiratory pressure in pressure modes and biphasic modes is defined in your ventilator, ask the manufacturer. 2 applications of the biphasic mechanism. Biphasic mechanism is mainly applied in mimicking traditional pressure and adaptive modes and forming unique biphasic modes. DuoPAP and ARPV are 2 typical biphasic modes. The 2 modes may be merged into one. DuoPAP mode. DuoPAP mode is also known as BiPAP mode. In this mode, PEEP automatically alternates between 2 set PEEP levels in a set time pattern. The patient can breathe freely at either level, with or without pressure support. This mode serves as a flexible platform for those who want to mimic traditional modes themselves, for instance, pressure SIMV mode. ARPV mode. ARPV stands for airway pressure release ventilation. It is indicated for active patients who require a worryingly high inspiratory pressure. Typical settings in ARPV mode have a long PEEP high time, serving as the baseline for the patient's spontaneous breaths, and a very short PEEP low time, helping CO2 elimination. Its perceived advantage is to avoid excessive peak airway pressure, while maintaining adequate ventilation in treatment of severe ARDS patients. Its claimed disadvantages include potential volatrauma, and increased work of breathing and energy expenditure. Modes in Hamilton medical ventilators. All Hamilton medical ventilators can be roughly classified into 2 groups, namely Group A and B. Group A includes Hamilton G5, S1 and Galileo ventilators. Group B includes Hamilton C1, C2, C3, C6, T1, MR1 and Raphael ventilators. The modes in Group A ventilators are based mainly on the classic mechanism. The modes in Group B are based mainly on the biphasic mechanism. The table lists the given names of traditional modes in the two groups. The paired modes in the table are the same in breath types, sequence, control parameters and clinical applications. From a clinical perspective, the paired modes are more or less the same. This knowledge allows you to switch freely between Group A and Group B ventilators. For instance, a patient who is ventilated on a Hamilton G5 can be switched to a Hamilton T1 ventilator for transport. If you have a Group B ventilator, you can choose which mode names to display through the configuration. Mode names and various ventilator brands. In the real world, the ventilators in an ICU or a hospital often come from different manufacturers. Chaotic mode naming is rather confusing. In this table, traditional modes and biphasic modes in 6 popular ventilators are grouped by nature. All the modes in the same row are very similar, although there may be minor technical differences. With this table, you can easily see how a traditional or biphasic mode is named in different ventilators. The last column lists the mode names suggested by our Chatburn. When using this table, keep the following in mind. Genuine SIMV modes are not included. The manufacturers may change mode names and/or introduce new names. Bedside ventilation mode selection. Every mode has its indications and contraindications. There is no bad mode, but improperly used mode. This section provides some useful tips on mode selection. Before talking about mode selection, keep in mind, talking about mode selection is meaningless if the ventilator system is not functioning properly. Optimal mechanical ventilation requires not only proper mode, but also other ventilator settings. Patient's breathing activity status. Regarding mode selection, the first and foremost factor to consider is the current status of the patient's breathing activity. During mechanical ventilation, a ventilated patient may be in one of 3 possible statuses: passive patients, who do not have any breathing activity; partially active patients, who have weak and/or unstable breathing activity; active patients, who have strong and regular breathing activity. Patient breathing activity can change from one status to the other gradually or quickly, for instance, use or withdrawal of sedation. The table shows where an individual mode should and should not be used. As you can see, every mode group has its intended use. Improper use means that it is used beyond its intended use. For instance, a passive patient is ventilated satisfactorily in a SIMV mode. After a spontaneous breathing resumes, he may start to fight the ventilator. The battle may be ended by switching to pressure support mode. Which mode type is preferred? Every traditional mode category has 2 or 3 mode types: volume controlled, pressure controlled, and adaptive controlled. Which one should be selected? In passive patients, there may be little difference between the 3 modes. In active patients, pressure modes are preferred because they allow ventilated patients to control more aspects of mechanical breaths. This means more patient comfort and less likelihood of patient-ventilator asynchrony. Adaptive modes are very similar to pressure modes. If the target volume is set and adjusted both properly and promptly, adaptive modes may be superior to volume and pressure modes. Staff familiarity. If several suitable modes are available, first consider the mode that you and your colleagues know the best. Introduction of a brand new mode can be beneficial only when all staff members have been sufficiently trained. Future of mode selection. For optimal mode selection, you need not only to know what to do, but also to act in a timely manner. A clear tendency in this regard is technical automation. Let the ventilator select mode, more precisely the breath type, whenever necessary. Automatic breath selection is already realized in ASV and INTELLiVENT-ASV modes of Hamilton Medical. As a result, we do not have to worry about patients' breath activity status anymore. Conclusions. This learning module provides basic information about ventilation modes. The ventilation mode is a part of the ventilation settings. By definition, a mode is a predefined set of breath types and sequence for a particular ventilator behavior. Every mode has its indication, which is primarily based on the status of a ventilated patient's breathing activities. Every mode has a unique set of control parameters. Ventilation modes can be roughly classified as traditional modes, advanced modes, and biphasic modes. We have looked closely at the traditional modes, their breath types and sequence, indications and controls. We have also learned about the biphasic mechanism, which can be used to form some traditional modes and biphasic modes. The terminology of ventilation modes is not yet globally standardized. We have provided a table, which tells you how a mode is named in different ventilators. Finally, we have provided a few practical tips for bedside mode selection.